morning, everybody. So how did you like the keynote? How did you like the mouse listener and the mouse event? This was my favorite. My name is Mark Hoffmann. In my spare time, I work on the Chacoco code coverage library and on the Eclipse plugin. Some of you might have used it before. And these tools are based on Java bytecode. It basically instruments your classes under test and adds some probes to the classes. And based on that, we can create code coverage report and can see which parts of your code under test has actually been executed. And so we have to understand the bytecode and has to rewrite the bytecode. So for this, you really have to understand always the latest and greatest feature of the JVM specification. Whenever they add a new version, new features in a version to the Java bytecode specification, we need to catch up with the code coverage tools. So sometimes you discover funny new things about the specifications. And one of the discoveries I made about the implementation of Lambdas, we have a look today. If you look at a particular feature in any programming language, or especially Java, you always look at it on three different levels. Like you have the source code. There's some syntax for the source. It is compiled to class files, the Java class files. And the class files are executed somehow in the runtime. For today, we focus on the class files in the runtime, not so much about the source. I hope you're all familiar with the ideas and the concepts of Lambdas. Maybe you have been to the tutorial the day before yesterday or yesterday. If not, it might get tricky for you the next 30 minutes. Just as a warning. Okay, to warm up, let's see how we can actually write down Lambdas. These are these kind of anonymous functions we can write down here. Like this for each loop prints every single item. We can't see a type here actually directly. We can also write it down like this, like use the method reference, and we still can't see any type here. But we can make it a little bit more explicit using a local variable. So in this case, the for each method needs a consumer interface, and we can do a local variable. Now we see, okay, somehow the Lambda maps to an interface internally, technically. These interfaces are called functional interfaces. They have the property that there's a single abstract method. In Java, we have strict types, actually. In other languages, there are like methods handles or method references in Python or JavaScript. You can directly invoke the function object. And now in Java, it's not like that. The syntax is obviously not that nice because you still can't invoke directly the function object, but you have strong typing also for the function objects. And we use an interface, and we use basically the one method within, the single abstract method within to define the signature of this Lambda. So this fits nicely in the concepts in Java we already know, because we can now pass around this Lambda just as an interface implementation. We could do the same with inner classes. We can also create a consumer instance with inner classes. We will see the difference to the Lambda implementations also in the details. In this case, what always happens here is that we get an implicit capture of the surrounding instance. Even if you don't need it here at all, you always get a new instance of consumer and even capture state of the surrounding class, which could be really nasty, especially if it comes to serialization. We see more about that later. The first step, if we compile a piece of Lambda code into class files, is a process called desugaring. So if we consider Lambda as syntactical sugar, they called it desugaring to create actually something out of it which the JVM already knows. And the only container the JVM knows to execute code are methods. So if we decompile that, the class which contains this Lambda, we will find new synthetic methods, typically static methods, and they have the name lambda $0123 there, just enumerated. And they actually have exactly the signature we expect here, it's like a string item, and they do what we expect. So they get the system out stream and do println, invoke println on it. This is where actually the code goes to. The next question is, so how do we actually get some instance of the Lambda? We somehow need the consumer. And if you look at the bytecode at this point, where the Lambda instance actually should be created, we find something interesting. So this is where it is called. This is our for each invocation. And just a line before, can you read that behind? Is that readable? OK. Just a line before, there's an instruction called invokedynamic, and invoking a method which somehow returns the consumer. So this is what we actually need, the Lambda. And here's a pointer to some structure called, with the index 0, invokedynamic structure. So what is that invokedynamic? In Java bytecode, since Java 6, we had 4 ways to invoke methods in Java bytecode. It was invoke virtual, to call any instance method, for example, println on the print stream. Invoke interface, to invoke interface methods. So if the method type is bound to our interface, like runnable, we can call static methods. The opcode is called invoke static, like system exit. And invoke special is reserved for special methods like constructors, which are also methods within the Java bytecode, like the init method or the CL init, class init, the static initializer of classes. Those are invoked with invoke special. What we see for all of them is that they are statically typed. So at the time when we compile a certain class file, we already need to know the class where the method we're going to belongs to. Maybe not the implementation class, but at least the interface. So we can't just, like in JavaScript, bind any method. We have to make an upfront decision, what will this method be bound to? And this does not fit very well to the new kind of dynamic languages we see with like Python. And so a new opcode was added called invokedynamic. Interestingly, this was already added in Java 7. So this was already there in Java 7, but it was not used by the Java language itself. It got used now by Lambdas in Java 8, you will see. To make a short demonstration how the invokedynamic works, I picked that picture. So invokedynamic adds a new level of indirection if you call a method, like a DNS server. So if you first carry the name, and then you get the particular implementation, the IP address of the target host you want to connect to. Because I didn't find a nice picture of a DNS server, I used the telephone operator here. And this is how you used to initiate a call. So if you want to do a call, you did like invokedynamic and ask the operator actually to connect to. And the operator in terms of invokedynamic is a so-called bootstrap method. This is a static method you can ask to actually create a data structure called call-side. Call-side instance is basically a handle to a target method, the actual target method. So once it is connected, you can directly talk to your target method or the one you want to call, and the operator's out of the game. But initially, you need the operator to find the target methods. If you look at a little bit more in the technical details, the dynamic call side, this is where the invokedynamic is actually placed in your bytecode. There you provide a huge structure of parameters and optional parameters which specify, first of all, the bootstrap method handle. There's a new type, a new constant pool type since Java 7, method handles, which basically refer to a type and a method and a signature of a method. So you can address a method as a data type. There's also a representation in the Java API called method handle now, since Java 7. So we need to specify the bootstrap method, so the operator who knows. We need to give a method name for the method which should be created. We give a method signature. The signature is basically the parameters and the return type. And then we can also add static arguments. Static arguments are any arguments which might be specific to this particular bootstrap method we're calling. All types of the constant pool can be used here. like string, integer, long, float, double, and also the new types like method handle. This is important, we will see later, for the Lambda creation. On the other side, when the bootstrap method gets called, you get all these parameters. Just the first one you don't get, because you are the bootstrap method now called. You get a reference to the caller called lookup. Basically, you need that whenever you create new methods and new code. You need to know the context of the caller, like the class loader and stuff like that, and you need to make references to methods in the context of the caller. That's why you get this handle, this lookup handle here. Using this for lambdas, there is an API in the JDK since Java 8. The class is called Lambda Mechanics. This class is not designed to be used directly. We can see an example later on how you can use, but this class is basically used by the compiled class file. So the compiler relies on the fact that this class exists in your Java 8 JDK. It can also be used by other languages. It's not bound to Java language. Other languages can use the same mechanism. They're very generic implemented in here. And so why is it called meta factory? Because it's a factory for functions which create lambda. So it's a bootstrap method which returns a function which in turn creates a lambda instance. That's why it's called meta factory. Any questions so far? This is the API of the Lambda Meta Factory. If you recall the parameters I just listed, this is the caller. This is the lookup context of the invokedynamic call site. This is the name of the method we want to create. This is the third one is the type, which is basically the signature, the return type, and the parameters. Then we get something, the method handle to the implementation method. If you remember the slide with the desugaring, so where your class gets, your body of the Lambda implementation gets compiled into your class with Lambda $0, this is basically a handle to the actual implementation of the Lambda body. And this is another type which is typically the same as the SAM method type, so the type of the interface we're going to implement. But it could differ. It could differ. We see later if we do some magic with bridge methods. And that's a very generic version of another version of the same method in the Lambda Meta Factory, which has an var arg array here of objects. And if you read the Java doc, you can provide a bunch of different types and methods, different argument types here, and fine-tune the behavior of this Lambda Meta Factory. Actually, the signature is only known by the compiler, or should be known by the compiler. It's specified, but you don't use it directly. This way you can create serializable lambdas. You can add additional marker interfaces to your Lambda implementations, or sometimes you need to create so-called bridge methods. I have lots of code and example for you later on. If you try to understand how everything works, you could actually use the Lambda Meta Factory directly. This is some example code here. Disclaimer, please don't do this in your production code, and at least don't blame me. It's not the way how it is supposed to be used. So you can create all the parameters of the Lambda, basically call the Lambda, the Meta Factory method, to get this call site. From the call site, you can actually invoke the factory method then. This is the Meta Factory, this is the factory, and we get back our consumer, the printer, and we can again print our the content of our. This is what happens behind the scenes. It's not very efficient. I show you why in a second. And it's definitely not something you want to see in your production code, but it might help you to understand how everything works. By the way, there's a GitHub repository with all the example code. You can just get the example code and play with it. I have a link on the talk description, and also at the end of the slides, you will see all the references and all the links to read more about whatever I'm presenting here. Why is that not very efficient, besides the fact that it does not look nice? So just to recap the Lambda creation process. We have some invokedynamic call site. The invokedynamic call site needs to call the bootstrap method. The bootstrap method needs to create some Lambda implementation We will see more in a second. It needs to create a factory method, actually, to create instances of this implementation. We need to link to this factory method from the call side. We need to call the factory method, and we need to create a Lambda instance. Somebody is claiming that this is has way more better performance characteristics than inner classes. The reason is that this is only created once. This is the magic about the invokedynamic, that the resolution process of calling the bootstrap method only happens once at the first time when you call the method. So all that's left is actually just call the factory method, and this is as fast as calling a normal method in Java. So this is all this overhead here is just for the first invocation. Afterwards it's gone, and it's as fast as calling a normal method like with invoke virtual. So how is the Lambda implementation actually created, and how does the Lambda implementation look like? Let's start some reverse engineering. If I don't know how I got to a particular point in my program, I can do something very simple and just throw an exception and see how I came here. Let's do that. Okay, I see my for each loop. I also see my de-sugared Lambda body implementation, Lambda $0. And then I see something really funny here, which is a class called $Lambda $1 / blah, 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 accept. And this is somehow a bridge between the consumer I need and my Lambda implementation. And this is actually what the Lambda meta factory creates for us. It does it by on-the-fly creation. It's not created by the compiler. Unlike inner classes, you can't see them in your source code, or you can't. There's no type. You cannot make a reference to an inner class. But this code for the Lambda is actually created on the fly within the runtime of the target virtual machine. The code then is defined to a so-called anonymous class. There's the famous unsafe API within the Java runtime, and JDK uses it at all places where they have to do some dirty stuff. In this particular case, they create a class without actually using a class loader. And there's an internal debug option. It's no official API, but if you dig to the implementation code, you can set a system property to actually dump the proxy classes. So you get class files on your disk, and you can study the class files and see what the Lambda implementation does for you. What do we need in the Lambda implementation classes? First of all, we need the SAM implementation. I mean, that's why we do everything. We might need so-called bridge methods. We'll see later what this actually is. We might need a constructor actually to capture, retrieve the capture if the Lambda captures some state of the local variables. We need some members, obviously, to store the capture, and we need the factory method. The factory method which actually creates the Lambda afterwards. And what they do, they implement the factory method right in this class. They have to generate anyways. We can decompile these classes, of course, if we do this internal option. What I did for some reverse engineering is, I mean, it just used reflection. Like I looked at the toString method, at the class name, what modifiers does the class have, what superclass do we have, what are the interfaces, the class loader, what fields do we have, what constructors do we have, what methods do we have. Now let's step through some examples. Let's start with the very easy one. Like we have a very simple Lambda which does not capture any state at all. It just prints user system out print line. And if you look at the properties of the Lambda implementation, which is created for this Lambda, okay, it has the internal funny name, which is due to the fact that we use this unsafe define anonymous class method. It's pure implementation detail of the JVM. You cannot reference it at all. It will have, with every start of your application, it will have a different ID even. The class is final. Okay, makes sense because we can't subclasses at all. It's derived from object. It obviously implements our Lambda interface, the Lambda type. This is why we do everything. It also has the method. we're looking for, the run method, obviously, of the runnable interface. It needs a constructor. And the class loader is the app class loader because this is a class loader where it's a simple main program. This is where we came from. That's very basic. Let's see a little more advanced example. If we have lambdas with capture, so capture means we capture some local state, some local variables, and use them within the lambda. So we need to remember the state because the lambda instance can be used at any point later in time. So in this case, we remember this local variable, captured value, and while this looks a constant, indeed the compiler creates a capture out of this. So what do we need then? So we still have our interface runnable, of course. We still have the run method. But now we have two more methods. One is a private field. First of all, we need the field. This is the field which holds the capture. So the state which is enclosed within the lambda. We have a constructor. The constructor actually accepts the value. So for every value we capture, we get another argument to the constructor. And then there's a static method which returns a runnable and accepts a string. This is actually the factory method, which we finally invoke. So the factory method, we put all the state for the captures on the stack, call the factory method, we get back an instance of the lambda, which has the behavior and which has the state we captured. Any questions so far? You look confused. There's an interesting thing about serialization. Have you seen the syntax before? Did you know this is possible? You can actually cast to multiple interfaces. It's very much possible. And the only purpose I did this here is because I want to give the compiler a hint that this particular lambda should also be serializable. It's not just a runnable. I might send it over the wire. So now here's the trick. If this lambda should get serializable, I need on the other side where I deserialize, I need the same class actually. But we just learned the class is generated on the fly. It's not just there. And it has a random name. So how to solve that? And from the very beginning when they designed lambdas, it was clear that they want to have some serialization mechanisms like you can have with inner classes. I mean, nobody recommends to serialize inner classes because you have a lot of implementation-specific state with inner classes. For example, if you reorder the arguments that is captured by inner class, the class created as an inner class will have different parameters to the constructor, so it will immediately break. It can even easily break in a way that it deserializes, but it has the wrong behavior. Like if you capture two integers, and if you flip them in your source code, if you recompile it and you have two versions of your application running on both sides of the wire, the actual values get flipped, and you won't realize. So it's very, very dangerous. And if you use Sonar or tools like that, you will always get a warning if you use serializable inner classes. But the same requirement was for lambdas. So it's not a good way to serialize lambdas, but it should be at least possible. And this is the syntax actually to enforce it. What do we get here? Again, we get a lambda which implements the runnable interface. It also implements the serializable interface because this is why we did it. It creates a constructor. In this case, we do not capture any state, and it implements the run method. And here's something interesting. If you took a look at the serialization specification, there's quite a few hooks. And one of the hooks is the method write replace. So basically, this means instead of serializing this object, return another object which I'm going to serialize then. And this is a hook which is within the serialization framework of Java. And the idea is not actually serialize the state of this class like the like the fields and the state, the capture state, because the class itself, like this is the name of the class, it will change. It's very unlikely that we will have the same class on the other end of the wire. That's why there's another API object which is called serialized lambda. You find that in the invoke package. And this is basically a description of how to create a lambda. So it describes the interfaces, it describes the method name, it describes the signature, and it even, this is the point here, it has an array for the captured arguments. And if you look at the class, we've seen the write replace here. This class has the opposite, called a read replace. So when the class is deserialized, it does not return this actual object, it calls the read replace object. And the read replace object, again, uses a Lambda meta factory to create a new instance out of these arguments. What I have not tried, I guess there could be some security holes here. I mean, think you just create such a serialized Lambda and call read replace afterwards. What do you get in which situation? Are the call size and the handles and the visibility right in any situation? I'm not sure about that, so. If you want to do some hacking on the JDK and find the next security hole, I really recommend taking a look into this. Bridge method. Have you heard about that? Bridge method? How that come? That's something nasty. We can actually subclass interfaces. In this case, I subclassed the supplier with a string supplier. And when subclassing interfaces, I think since Java 5, since the generics, it's possible to modify the return type and give a more specific type to the return value. Internally, the JVM cannot handle this at all. The JVM always uses a fully qualified signature, which is the arguments plus the type of the return type, of the return value. So what internally actually happens is that we have two methods here. Like the get method which returns the object and the get method which returns the string. And if we create this lambda as a string supplier, so the type is inferred from this local variable, we get the following. We get actually two get methods. One get method is for the string, which is this implementation, and the other is object, which is from the superclass from the supplier. This is also something they had to consider when creating lambdas, because functional interfaces might look like SAM, like single access method, but due to the bridge method issue, you actually could get multiple method implementations with different return types. Speaking about performance, there are some strategies to actually reuse Lambda instances. In this case, we have a function which simply creates a Lambda instance from a static method. So this does not capture any state at all. So obviously, the Lambda we create always have the same behavior. There's no way to put any parameters in the behavior of this Lambda. And if we call this method twice and compare these both runners we get here, we will see that we get the same instance actually. And we also get the same class, obviously, for the same instance. If you remember the slides when we decompiled and inspected the Lambda implementations, when for the simple case where there was no capture, there was no bootstrap method or no factory method. Because in this case, the Lambda meta factory simply creates a so-called static, how's it called? It's a method handle which basically returns the same value all the time, like a constant handler or something it's called. So we don't need a bootstrap factory method at all because it's always the same instance. This is a simple case, and this is actually the case which Oracle always cites. This is where the performance is way better than inner classes, because this is the only case where we do not have to create a new instance on every invocation. And this is when they show the nice figures like 5,000 times faster. But this cases for me is not very likely because typically you have captures. I do the same code, but a little bit different. I create the same Lambda twice, so the same basically definition of the Lambda, but at two different call sites. And what happens here is that we actually get two different Lambda implementations and two different instances. So the Lambda runtime has no chance to actually compare, to find out that these are the same implementations and we can share some instance. There's no pool for that, but it mustn't make sense at all. I mean, this is just another instance. It will not cost any additional overhead. For capturing Lambdas, it's interesting. So now we have one call site where we capture state. Here, we capture the state. It's interesting, eh? This is the reference to the the value of the static variable. So we capture actually the state here. Please remember that. I have a trick question for you in a second. And if we call this method twice, we actually get the same class because it's the same call site. So no need to create another class for every invocation, but we get different instances, of course, because theoretically the captured value here could be different, even if it's static variable right now. So, and here's the trick question, the bonus question. What is the difference here? So you see that? Use this nice syntax and this syntax. So what will be runnable 1, runnable 2? Will it be the same class, first of all? Any ideas? Will it be the same class? Yes, it's the same call site. Okay, that's easy. It's the same class. What about the instance? Will it be the same instance? Same class? Any other? Is there any capture going on here? Actually, it looks like, but it's not. It's not. This is really tricky. So at this time, we capture the value of we bind actually the method to the value to this instance of the print stream. In this case, it's just a static block, and every time it is called, it catches the actual value or the current value of this static method. So it's actually the same here. There's no captures going on here. Okay, I think the time is. We have some more minutes for questions. I put a lot of references if you want to dive into this on the slide, and also I just updated the talk description. You'll find all the links on the site, especially a small Git repository with executable examples. You can execute all the examples. There's also excellent talk by Brian Goetz, which is 1 hour, which gives also a lot of reasoning why they designed it this way, and he also discusses about options, what could have been another way to actually implement it. We have some time for questions, and then please help the organizer to collect some feedback for the conference and fill out the feedback form you find directly if you log into eclipse.org, eclipsecon.org, and select the talk, the only red one today, and just write in whatever feedback you want to give to the sessions and also to the other sessions. Okay, thank you. Questions?
Can you go back to the slide where actually the string was captured after the invocation? I don't know. Earlier?
For the method,
There was a string capture.
here, this one, yeah. The bytecode.